Okay, welcome back, everybody. I just want to remind us what we did last time. Last time we talked about, what did we talk about last time? Uniform continuity. Yeah, so we've been talking a bit about what it means for a function to be continuous. And you saw many definitions of continuity. And one of them was a metric definition. So it basically said that a function's continuous means that close enough points get mapped to close points. So if in the target you want to be epsilon apart from the image of a point f of p, then in the domain you want to be delta, at most delta apart from p, right? Okay. Now, of course, for a general function, in the domain, that target delta might depend on the choice of point p. Okay? And the whole idea of uniform continuity is that that delta doesn't depend on p. Okay? So the function uniformly spreads things apart. Things that are no more than delta apart get sent to things that are no more than epsilon apart, no matter where you are in the space over here. Okay? Okay, good. So that was the idea of uniform continuity. Today I want to say a little bit, in the first part of this lecture anyways, about discontinuous functions. And you might wonder, what in the world is there to say about discontinuous functions? They're just functions that aren't continuous. Yeah? Okay, well, turns out there's actually more interesting behavior than just saying that a function's not continuous. There's a lot of interesting things you could explore. And the first example of a function that's not just not continuous, but highly discontinuous is something we'll call the Dirichlet function. So it's a function that's, in fact, not continuous everywhere. Okay? Very simple example of a function, however. So we'll define it to be, let's say, f of x is 1 if x is rational, and let's let the function be 0 if x is not rational. And so you can see what this function looks like. It's basically either 1 or 0, and you can see all the places where it is 1. It's 1 at lots of places. And it's 0 at a lot more places. Okay, so rationals are 1 and irrationals are 0. Okay. Now you can convince yourself that f is not continuous anywhere, at any p. Why is that? Give me just a brief argument. Emil? Okay, good. So a very easy way to see this is no matter what point you pick, if you take a ball around it, that's an open ball, it'll contain rational and irrational points, right? So whatever where's its image going to be, it's going to contain points that are close to 1 and close to 0. So if you pick epsilon less than a half, then you will have trouble satisfying the definition of continuity. Okay, good. So this is clearly not continuous, and it's a mildly interesting function. Okay. Okay. This one may be a little more interesting. Suppose I did the following. Let's consider the following example. So this is the one that actually you're going to explore in your homework. It's another example of what's a kind of Dirichlet function. But I'm going to, let's define it to be 1 over q if x is rational of the form p over q in lowest terms. A little more interesting. Okay? And let's define it to be 0 if it's irrational. So if x is irrational. Okay. Well, how's this function behave? Let's see. Help me out. What is this function's behavior at 0? Lowest terms? 0 over 1 is the low. Yeah, so its value should be what? 1. Okay. Good. What is its value at 1? 1 over 1 is 1. Good. What is its value at a half? A half. What about its value at 3 halves, if I were to do that? A half. Okay. Okay. What about, let's do the quarters. How about at the 1 quarter and 3 quarter? Yes, it's a quarter at both of them, yes? In fact, it'll be a quarter even at 5/4 too, yes? Would you agree the stuff beyond 1 kind of looks like the stuff between 0 and 1? So I'm just going to, I'll stop thinking about what's going on there. But, okay. Let's see. What about a third? A third is here. Okay, yes, you're right. And 2/3 also behave similarly, yes? Okay, interesting. Okay, well, it's a very curious function. What about, oh, let's just do a few more examples. How about an eighth here? And what about 1/8 and 3/8? And 5/8? And 7/8? Etc. Okay, do you get the picture here? So this function has a different value for different rationals based on the size of its denominator in lowest terms. It's a very cool function. What do you notice? Let's see. If I take any particular value, how many times does this thing go above that value if this value is somewhere bigger than 0? Only finitely many times, right? Okay. Oh, interesting. So, very interesting. So if my target were to look at an epsilon ball around 0, suppose I look at an epsilon ball around 0, how many times does this function leave the epsilon ball around 0? Finitely many times, no matter what epsilon is, yes? Would you agree? Oh, okay. So this function, what is it doing at the rationals? Well, it's doing something non-zero, and would you agree it's pretty clear at the rationals this thing is not continuous. What's happening at the irrationals? At the irrationals, let's take an irrational value here. How about this point right here? Square root of 2 minus 1. There. What's happening at this point? Well, its value is what? 0. Yes, indeed. And is there a neighborhood around it which will land in this target epsilon window? If there's only finitely many times it exceeds? Yeah, what neighborhood? How small are you going to make delta? Well, there are finitely many rationals where it exceeds. So take the minimum the minimum distance between that. So you have a delta ball for every epsilon. So this function is the amazing property that it is actually, while it's discontinuous at all rationals, it's actually amazingly continuous at all irrationals. An amazing function. So in fact, you see the set of discontinuities is It's a countable number of discontinuities, and it's continuous everywhere else. Okay. Here, the set of discontinuities is uncountable. It's everything, right? But what's interesting is where it's discontinuous and where it's continuous doesn't have to comprise an interval. Yes, Jenny.
Is there a function which does it the other way around, which is like continuous on all continuous on all rationals and discontinuous on all irrationals?
Oh, interesting. What do you think?
Seems like there should be, but I think I should
Interesting question. So the question was, is there a function that is continuous at all rationals, but discontinuous at all irrationals? What do you think? How many people say yes? How many people say no? Oh, so now you've changed your mind, Jenny? Very interesting question. I'm going to let you mull over this, and I think you'll have the tools to answer this question very, very soon. Okay. Interesting question. Okay. So let's learn something about discontinuities. Maybe it'll shed some insight as to what's happening. So we can try to classify discontinuities. So if you have a function, let's say from an interval into the real numbers, let's make a notation. Well, here's one kind of discontinuity you might have. You might have one that looks like this, sort of a jump discontinuity, right? It's a very simple kind of discontinuity. Okay, at say some point x. And maybe the value here is q, and the value here is q prime. Okay. So notice in this picture, if I were trying to describe what's happening here, it's certainly the case that if I were in between, let's say, if I were in this, if I took some sequence on the right here, and I followed the images of these points, the TNs, what's going to happen as the sequence here, the sequence of points converges to x, to the images? What's going to happen? Yeah, it'll approach q, so we can actually give this thing a name. So notice that for all sequences Tn in, let's say, x comma, okay, let's call this A and B, in x comma B, with Tn converging to x, we have f of Tn converges to q. Okay. So we'll give this a notation. We'll say here, we'll write, one way to say this is f of x plus, we'll let that be q. In other words, this is saying that the limit as t approaches x, but from the right-hand side, that's another notation, t going to x plus, of f of t is q. Okay, so we'll have a notation that says, describes what's happening here. So this thing actually has a right-hand limit, but it doesn't have a limit. But if it has a right-hand limit, then we'll use this notation. And similarly, we can say from the left-hand side, I won't rewrite everything, that f of x minus, I'll say is what? Maybe q prime, which is basically what I mean to say here is as t approaches x from the left, f of t is also q prime, excuse me. Okay, and of course the point of our discussion earlier about limits is that the actual limit, t goes to x of f of t, exists if and only if what's true about f of x plus and f of x minus. They're equal. Excellent. Okay, so that's just restating something we said before. So if these things exist, we'll say that this function has a discontinuity of the first kind. Yeah, so if these exist but not equal, we'll say f has a discontinuity of the first kind. Sometimes people say a simple discontinuity. Okay? Yes?
Do people ever write an equivalent that, like, would you ever use, like, half delta balls to talk about this? Or people always talk about it using sequences?
Oh, I only chose sequences as a way of thinking about this. You could certainly define it just in terms of the usual notion of limits on a half ball. Yeah, that's fine. Yeah, okay. And if it's discontinuous but not of the first kind, then we say it's of the second kind. Okay, good. So else we say second kind. Okay. So one question you should ask yourself is, are there discontinuities of the second kind? Yes.
What if it's one of those where the limit exists, but the point to which the limit is going to is not? So if you have a function and say f of x is q, but the limit as it goes to x is q prime from both sides?
Yes. Yeah, so if it's like this, right? Yeah, actually this should still be included as first kind. I guess. Thank you. This is actually what I get for departing from my notes. So they could be equal, but the function value could be similar. So let me correct this the way I have it in my notes. So if f is discontinuous, there, but f plus and f minus exist, but f of x plus and f of x minus exist, then we'll say f has discontinuity of the first kind. And that will actually include, thank you, that will actually include this picture. Because on both sides they exist, but it's still discontinuous. Okay? Thanks. Yeah. Basically, we want first kind to mean kind of a silly kind of discontinuity. Okay. Okay. So what about other kinds of discontinuities? Are there discontinuities of the second kind? Well, of course there are, otherwise we wouldn't have a terminology for this. But what's an example where, give me the condition that would have to be true to be a discontinuity of the second kind? Maybe the limit doesn't exist, right, on either side, right? So here's an example. You can have an example like this, and so here's the function from R to R. On one side it's doing something like this. Other side it's doing something like this, a topologist sine curve like last time. And then at 0 we'll make it 0. And on the right-hand side, this is, if you like, f of x is 0 if x is less than or equals 0. And let's make it sine of 1 over x if x is bigger than 0. So in this case, at 0, there's a discontinuity of the second kind. And which limit does not exist? The one coming from the right. Thank you, Maya. Okay, good. So let's come back to these examples here. For the Dirichlet function, what kind of discontinuities do we have in this picture? Discontinuities of the second kind. You guys are giving me the peace symbol. Peace. Peace. Okay, good. So in the original Dirichlet function, all discontinuities are of the second kind. Okay, good. What about here? What kind of discontinuities do we have here? It's continuous at all irrationals and discontinuous at all rationals, and there's discontinuities of the... Okay, how many people say that the discontinuity at 1 is of the second kind? How many people say it's of the first kind? How would we show that? Show that the limit exists coming from the right. Now, don't you agree there's lots of rationals and irrationals here as I move in? But, yeah, well, notice that if you give me one of these little epsilon balls, I can find a little delta ball around here that it's within that epsilon, right? Of 0, which is would show that on the right-hand side, this thing has a limit of 0, right? And on the left. So, in fact, in the second example, the second Dirichlet function, the 1 over q Dirichlet function, all discontinuities are simple. They're of the first kind. We say simple is another way to, the term that we use here. Okay, so we've changed the nature here of the discontinuities. Let's do another example. How about the following? What would you say is true about... We can have some fun here. How about 0 if x is irrational, and x squared if x is rational? What kind of function is this? So a lot of irrationals, it's 0. And if it's rational, then its value is x squared. So what does that look like? Okay, what kind of discontinuities do we have? First of all, where are the discontinuities? Every point except possibly 0. That's where you might be worried. Is it continuous or discontinuous at 0? Let's see. To show that it's continuous at 0, let's show that, in fact, around 0 and its image, which is 0, for every epsilon ball, there's a delta. There's an epsilon ball. There's a delta around which, if you're within this delta, you're within the epsilon. True? Yes. Okay, good. I won't make you write it down, but it's certainly true. So this thing is continuous at 0. Very good. And what are the nature of the other discontinuities? Are they all of the second kind? Yeah, let's see. How would I verify that? Well, if I were near some point here that is irrational. Does there a limit exist on one side or the other? Well, no, because I always have rationals within any ball. What's the proposed limit? Well, yeah, I could be outside of that ball if here, let's do an example. Take this point, whose value is here. This is some rational r in Q. Okay, so I want to know, does it have a limit coming from the left or the right? Well, the only possibility is that the limit coming from the right is 0, right? I mean, it could be, you could test all the other ones, but it's pretty clear it's not going to be anything else. It's only, I guess maybe you want to test this point and this point. But in either case, there is no delta ball that will leave you within epsilon of this proposed limit, or what about this one? Not this one either, right? So these are discontinuous at 0 and second and discontinuities of second kind at all other points elsewhere. Okay, good. So we have some idea of what simple discontinuities are and what crazy discontinuities are. Okay. Well, there are some cases in which we can say, we can restrict the kinds of discontinuities that can occur. And so this leads us to the topic of monotonic functions. So monotonic function basically means either monotonically increasing or decreasing. So we'll say it's monotonically increasing if any time x is to the left of y, this implies what about f of x and f of y? Is less than or equal to? Yes, this is all functions from an interval into R. So we can talk about, you're basically going from real numbers to real numbers. We're going to say f is monotonically decreasing if x less than or equal to y means what? F of x is bigger than or equal to f of y. Right? Okay, good. So let's see. What can we say about monotonic functions? Well, here's an example. Suppose I have, let's give an example of monotonic function. Here's one. Certainly that's monotonic, yes? Okay. Okay. Are you prepared to make any kind of conjecture about the kinds of discontinuities a monotonic function could have? Only simple? Is there any way a monotonic function could have a non-simple discontinuity? Some people say yes. People say no. Okay, yes, okay. Good intuition. So in fact, that's our a theorem. So if f is monotonically, let's say, increasing, the proof for decreasing is similar, on, let's say, an interval AB, then I claim that this actually means that f of x plus and f of x minus exist at every point for all x in the NAB. Let's see if we believe that. Why do we think that's true? What's an argument? Yes. Yep. As x approaches from the right. Yeah, pluses for me from the right and minuses from the left. Okay. Now you have me wondering whether I agree with what's in the book, but let's take this to be plus from the right and minus from the left, because that's sort of what the notation indicates. Okay. Okay, what's the idea here? Why do these things have to exist? Yes? Yeah, the same ideas should work for decreasing as well. We're just going to take one case here. Why is this true? It feels right. Why is this true? Well, I claim the following. I claim, in fact, something more is true. Would you agree that, maybe this should help us see why this is true, that whatever the value of x is, it has to live between would you agree that whatever this value is, it has to live between the value of anything on the left and the value of anything on the right, yes? Okay, by monotonicity. So if I look at all the values it achieves on the left and take their supremum, it should still be at least as big as that, right? And if I take all the function values on the right and look at their infimum, then the values, this point should be less than or equal to that infimum. So certainly this is true of ft, where, here I'll just write like this, where t is on the right, t is in xb, and this will be the supremum of t, where t is in ax. So that should be clearly true, right? Okay, so of course I've just said sup and inf here, but how do we know the supremum exists? Help? It's bounded. These values are bounded by f of x, right? So we're okay that this exists because it's bounded. Okay, bounded above and bounded below, similarly here. Okay, so there was no problem in saying that. Okay, so does that help us? Does that give us some idea of what's happening? Let's see. So, what's the idea? Let me redraw this picture here. Suppose I have a monotonic function, and let's take a point x. And in fact, if you don't mind, I'm going to call this supremum. If you don't mind, I'll call this supremum A. Let's call it A, which is the supremum of all the values on the left. Okay. And now I claim A is going to be I claim that A, in fact, is going to equal what? What do you think I'm going to claim? Yeah, I'll claim that it's f of x minus. Okay. So let's see here. Let's draw ourselves a picture. Here is x. Here is, maybe it's doing something like so. Here is f of x. But the supremum of all the values on the left is going to be this number a. Okay. And so all I have to do to verify that it's in fact f of x minus is to show you that the limit of all the values coming from the left is in fact this number a. Well, let's take an epsilon ball around A. You give me an epsilon ball around A. Doesn't matter whether it contains the other side or not, but if I look at A minus epsilon, well, then we'll just make an argument there. So given epsilon bigger than 0, consider A minus epsilon. Well, if I look at this number A minus epsilon, certainly there's some values that of f of t that are bigger than this because it's a supremum. So there exists a delta such that f of x minus delta is bigger than A minus epsilon and less than or equal to A by the definition of supremum, since A is a sup. Okay. Now that means that there's at least one point that I can find to the left whose value lives in here. Can I show that all the points within some neighborhood on the left must live in this epsilon ball? Yes, because the function is monotonic. So all the points in here have to be where? In between. So in fact, this delta works. So, but then any t in x minus delta x must satisfy f of x minus delta is less than f of t is less than or equal to a. So f of t is in the delta ball, is in a minus epsilon a, as desired. Okay, so that's the basic idea. The argument's similar for the other side. Okay. So what have we shown? We've shown this claim, similar argument on the other side. Okay, so the corollary to this fact that the f sub x plus and f sub x minus exist is, in fact, that monotonic functions have no discontinuities of the second kind. Oh, really? Okay, that's interesting. All right. Okay, well, let's see. This actually has a very interesting consequence, and that's the following theorem, which is also a very nice theorem. I claim that if f is monotone on AB, either increasing or decreasing, your pick, then the set of discontinuities what do I mean by that? The set of points where the function's discontinuity, set of points where f is discontinuous, is not continuous, is in fact countable if f is monotone. Really? Why is that? This is quite clever, actually. So if I look at a function that's monotone, then if it has discontinuities, they're basically jump discontinuities, aren't they? Right? They jump around, right? Okay. So why do you think there can only be at most countably many discontinuities, countably many jumps? This is a clever idea when you see it. Why does there have to be countably many jumps? Like I'm jumping from here to here, jumping from here to here to here. Let's see. Well, for every point, it has a left limit and a right limit that exists, yes? Okay. Yeah, so Aaron's saying, look, this point has a left limit and a right limit. Okay. So if there's a discontinuity, there's a gap here between f of x minus and f of x plus, right? It can't be like that picture. Yes, Lindsay?
Does that have to do with the fact that the greatest value has to be f of b for f of a, depending if it's monotonically increasing or decreasing?
Uh-huh.
You can't just keep like jumping forever, if that makes any sense.
Okay.
It's bounded within a certain region.
Okay, that's a good intuition, but why can't I just jump a lot in between? Paul?
On the first exam that the real line can't have an uncountable number of disjoint intervals.
Okay, very okay, good. So,
And so you're saying that each discontinuity implies this in existence of this kind of jump. So it would be contradictory to say that there could be uncountably many jumps.
excellent. So basically here, every discontinuity has a gap. Those gaps are intervals. Those intervals are all disjoint because this is monotonic. So you could pick a rational in every interval and associate a rational in every interval, and that would show that there can't be, it's the same proof, there can't be uncountably many disjoint intervals in R. So the proof idea is for all x where f is discontinuous, pick R sub x such that R sub x, let's pick this in the rationals, such that R sub x actually lives between f of x minus and f of x plus. Okay. So the thing to notice is that if you have two discontinuities, the R you pick is actually going to be different. So if x and y are both are in the set of discontinuities, let me just call this thing D. If x and y are in the set of discontinuities, R sub x does not equal R sub y because f is monotone. So what you'd have is a one-to-one correspondence between the set of discontinuities and a subset of the rationals. Nice. Okay. Okay. So what does this mean? Well, one of the consequences of this is, in fact, if the function that Jenny worried about actually existed, then that function couldn't be what? At least this theorem would say it couldn't be monotonic. If you're going to construct a crazy function that, in fact, is not continuous at, it's not this picture, it's the one I erased, that is not continuous at the irrationals, but continuous at the rationals, then it can't be monotonic. Interesting. Okay. Good. So now is actually a good time to take a couple-minute break, and maybe we'll talk about the exam after the break. That's probably the best thing to do.